Astronomers are taking a closer look at 3I Atlas, our newest interstellar visitor, and recent analyses are suggesting something remarkable. This object may be far older than our solar system. Its trajectory, chemistry, and radiation-processed surface all point to an origin deep in the Milky Way's past, possibly 8 to 12 billion years ago. It's a rare chance to study material from a completely different era of the galaxy. In this video, we will explore what makes scientists think 3I Atlas is so ancient and why it matters. Let's get started. The identification of 3I Atlas began like many routine surveys, a faint moving point of light captured by the Atlas telescope network. But almost immediately, the object distinguished itself through one defining measurement: a hyperbolic orbit. Its eccentricity, significantly greater than 1, confirmed it was not gravitationally bound to the Sun. Rather than looping back, it would pass through once and continue on its outbound path. That established the first key fact. 3I Atlas originated beyond the solar system. The next major insight came from orbital reconstruction. When researchers traced its incoming direction through galactic coordinates, they found it aligned more closely with the Milky Way's thick disk, a population of stars formed roughly 10 to 12 billion years ago. While a trajectory cannot pinpoint an exact birthplace, it can identify the broad region of galactic space the object most likely came from. The alignment suggested that 3I Atlas may have been formed in a planetary system belonging to this older stellar population. This immediately raised the possibility that the object is dramatically older than anything native to the solar system. Chemical observations soon added more detail. Using infrared spectroscopy, the James Webb Space Telescope detected water ice, carbon dioxide, carbon monoxide, and sulfur-bearing molecules in the comet's coma. These volatiles are easily lost when an object spends significant time near a star, so their presence indicates that 3I Atlas has remained in deep cold for the vast majority of its existence. This chemical preservation is consistent with an object that has wandered the interstellar medium for billions of years, undisturbed by stellar heating. The condition of the surface supported this interpretation. As the comet approached the Sun, it displayed signs of long-term irradiation, including a darkened exterior and an enhanced CO2/H2O ratio. These are classic consequences of cosmic ray processing, which gradually alters surface ices over extremely long timescales. The level of processing observed is difficult to achieve within a few hundred million years. It aligns better with gigayear scale exposure. One final clue comes from how interstellar objects become interstellar in the first place. Most are ejected during the early phases of planetary system formation, when gravitational interactions with large planets fling out smaller bodies. If 3I Atlas originated in a thick disk system and was expelled during its system's early, chaotic formation period, then the ejection likely occurred long before the Sun existed. Individually, these clues are suggestive. Together, they build a consistent picture. 3I Atlas is not just interstellar, it is ancient, likely formed in an environment far older than the solar system. The age of 3I Atlas matters because it offers something extremely rare: direct access to material formed during an early chapter of the Milky Way's history. Rather than examining this era through models or indirect observations, scientists can analyze the chemistry of a physical object that may date back to a time when the galaxy looked very different. One of the most important aspects of 3I Atlas is the chemical record preserved in its ices. The mixture of water, carbon dioxide, carbon monoxide, and other volatiles represents the conditions present in the protoplanetary disk where the object originally formed. If the parent system belonged to the thick disk, then these chemicals reflect a lower metallicity environment in which the dust, gas, and temperature gradients differed significantly from those of the Sun's formation region. Studying these signatures can help researchers understand how planetesimals formed under different galactic conditions. Another key area of interest is the effect of long-term cosmic ray exposure. Over billions of years, galactic cosmic rays break apart molecules, reorganize chemical bonds, and progressively darken the surface of icy bodies. Observing these effects directly on 3I Atlas allows scientists to compare theoretical predictions with real data, refining models of how small bodies evolve when they are not influenced by a central star. This also helps calibrate surface aging studies on solar system comets. Theories about 3I Atlas's origin vary, but many center on the idea that it formed in the cold outer regions of an early planetary system. Its volatile content supports this scenario. However, other aspects, such as its unusually high CO2 relative to water, could indicate formation conditions quite different from those seen today. Whether this difference reflects the unique chemistry of early stellar environments or simply the effects of extreme age remains an open question. 3I Atlas also contributes to broader discussions about the population of interstellar objects. If this body is truly ancient, it shows that planetesimals formed early in the galaxy's history can survive intact for billions of years. This suggests that the interstellar medium may contain many more relics of ancient planetary systems than previously expected. Each interstellar visitor, therefore, represents more than a single event. Collectively, they form a dispersed archive of galactic history. In short, 3I Atlas is scientifically important, not just because it is interstellar, but because its age and chemistry provide rare, direct evidence about planetary formation processes from an earlier era of the Milky Way. The study of 3I Atlas has implications that extend beyond understanding a single object. If interstellar visitors can carry preserved chemical records from different periods of galactic evolution, they become useful tools for reconstructing how planetary systems have changed over time. Instead of relying solely on models, astronomers can use these objects as physical samples from different epochs. One important implication concerns galactic chronology. If more interstellar objects turn out to be as old as 3I Atlas appears to be, scientists may be able to map the chemical history of the galaxy not only through stars, but through planetesimals. This kind of galactic archaeology could help reconstruct conditions in regions and eras for which no other direct samples exist. Another implication involves the survival of volatiles and complex molecules. The fact that 3I Atlas retains ices after such a long journey shows that small bodies can preserve primitive chemistry over enormous spans of time. This supports the idea that organic and volatile materials might travel between star systems without being fully destroyed. Understanding the durability of these compounds helps refine theories about chemical transport across interstellar space. The surface of 3I Atlas also offers a unique case study in irradiation-driven evolution. Observing how cosmic rays have altered its surface allows astronomers to compare it with solar system comets that have also experienced irradiation, albeit over shorter timescales. These comparisons help improve models for predicting the appearance and composition of future interstellar objects. In terms of ongoing research, scientists will continue monitoring 3I Atlas as it moves away from the Sun. Changes in its coma, dust production, and volatile release will provide additional data about its structure and composition. Each new observation helps refine its age estimate and clarifies the degree to which its interior has been protected from cosmic processing. Looking to the future, upcoming survey telescopes, such as the Vera C. Rubin Observatory, are expected to detect many more interstellar objects. With larger sample sizes, astronomers will be able to determine whether objects like 3I Atlas are rare outliers or representative of an older population of planetesimals. If many of these objects prove to be ancient, it would confirm that early planetary formation across the galaxy produced large amounts of long-lived debris. In this sense, 3I Atlas is not just a passing visitor. It is an example of how interstellar objects can serve as time capsules, preserving information about planetary systems that existed long before the solar system formed. Its value lies not only in its uniqueness, but in what it previews: a future in which interstellar visitors help piece together the deeper history of our galaxy. Three I Atlas is likely older than the solar system itself. Its chemistry and surface preserve a record of deep galactic history. A rare ancient visitor, passing through once and never returning.